Okay, guys, we're going to finish up the bottom of page 3 of our lecture notes and then move on to page 4, which we don't have much to do there, so this should hopefully this won't take very long. I did want to make one correction. In the last video, we talked about from the combined gas law problem. I gave the answer as 55 liters, and actually, when I look back at our material, we can have 3 sig figs. So the correct answer should have been 55.2. I think it was 55.19 is what I got. So I really should have reported that as 55.2 liters. So let's be careful about that. You know, I don't give you too hard of a time on that. However, on the problem that we did with the moles of gas in the lungs, where we said that it was 0.17, that was right because we only had 2 sig figs in that answer, and the answer came up like 0.166 moles. So we did round that to 0.17. So that's how we got that. Okay, so let's look at example where we got this solid potassium nitrate being heated. So this says 3.2 moles of solid potassium nitrate is heated and released oxygen and potassium nitrate. So right there it tells us what the products are. So we're going to be able to write a balanced equation for this. Calculate in volume the liters of oxygen obtained at STP. Now see, we know that we can't, with stoichiometry, we can go from moles to grams. But how do we do grams or moles to liters? Well, with the ideal gas law and then with Avogadro's constant, we actually can do this. But the first thing we do need to do is write our balanced equation. And so we're going to see that as this here. Okay, so we've got potassium nitrate. Whoops. That is awkward. Come back here. There we go. Potassium nitrate and our oxygen. So this is a solid, this is our gas, and then we get this. So 2 moles of this decomposes and gives us oxygen gas, and 2 moles of potassium nitrite. Okay, so this is plain old stoichiometry, right? So we're just going to say that we've got 3.2 moles of this, and we're going to use our conversion fact. We don't have to go to the balanced, we don't have to go to the periodic chart, right? We do have to go to the balanced equation, not the periodic chart because we don't have grams here. We start with moles, so you're just going to go to the balanced equation. So 3.2 moles, and this is our balanced equation ratio, right? So this gets us 1.6 moles of oxygen, right? So here we've got a couple of options. We could actually go to PV inert. And we could say, well, now that I have the number of moles of oxygen, I can calculate the volume of oxygen because I've got the other information. But what I want to note here, and you could do that. You could do that because it's STP, and we know what the values are for STP. But also at STP, we know that 1 mole of a gas has a volume of 22.4 liters. So we can take our number of moles of oxygen gas and use this conversion fact 22.4 liters is how much 1 mole takes up. So then we're going to, mole is going to cancel. So we're going to multiply, and we get, what is that, 36? We have 2 sig figs. So 36, right? 36 liters of O2 is our answer. All right. Okay, of O2. And now let's talk about Dalton's law of partial pressures. This says that all gases in a container contribute to the total pressure. So summed up, this is PT equals P1 plus P2 plus P3 plus P4. It just goes on and on and on, right? So we just add them up. The problems that we have to solve here are pretty simple if we don't let ourselves get carried away with what we're being expected to do. Okay, so the first one says oxygen is collected over water, and it has a total pressure of 713 torr at a temperature of 25 degrees Celsius. What's the pressure of the dry oxygen? So you're going to need to go look up the pressure of water, the water vapor pressure at 25 degrees Celsius. And you can do that at table 12.1 in your book. And then you're going to subtract that out, right? Because it's going to tell you that in torr. So you're going to take the total pressure, which is 713 torr, and say that's equal to the pressure of the oxygen plus this pressure of the water vapor that's been added there. So it's actually just going to be the difference, right? So the number that we get for the oxygen has to be smaller than the total pressure, but the oxygen's pressure and the water vapor skipper's pressure is going to add up to the 713 torr. So I get 689 for that pressure. Is that what you got? So that's how we do that. So try that deep sea diver example, okay? And it's the same thing. We've got a total pressure. We've been given two pressures. We're trying to find the unknown pressure. You could also take that pressure there and find the mole fraction of that gas. We're going to do that when we come back. I'm going to find us a mole fraction problem, and we're going to solve that, and that'll be the end of our videos for today, okay? All right, so you guys work that next problem there to find out the partial pressure of the oxygen for that deep sea diver, okay? See you.